Welcome to another example of relative motion. Here we have a plane that has an airspeed of 250 kilometers per hour. Note that airspeed is a relative velocity, which in this case is velocity of the airplane relative to the wind. So the airplane is flying through an easterly crosswind whose speed is 20 kilometers per hour. If the plane wants to maintain a direct northerly course, perfectly vertical up, what is the angle the plane must point into the wind? What is the angle theta as depicted on the diagram? So what I will do is I use letter A to represent airplane, and I use letter W to represent the wind. Therefore, V sub W is velocity of the wind, which is an absolute velocity. V sub A is velocity of the airplane, and velocity of the airplane relative to the wind, designated by V sub A slash W, is the given value of 250. So let's draw the two components of this green relative velocity vector. Observe that this arrow has a vertical component up and a horizontal component left. So this is vertical component of VAW. So this is VAWY component, and this is VAWX component to the left. So that's what we can see as far as the diagram is concerned. But let's go back to the basics of relative motion. The key thing in these types of situations is to know the relative velocity formula, and note that relative velocity of airplane with respect to wind is nothing more than absolute velocity VA minus absolute velocity VW. In other words, relative velocity is due to difference in velocities. Now, if I wish, I can rewrite this equation and solve it for VA and say VA equals to velocity of the wind plus relative velocity of the airplane with respect to the wind. Observe that this is a vector equation, so I can break it into two scalar components. Let's take positive to the right and write the x components of this equation, which I call equation number 1. Since we want VA to be perfectly vertical, its x component is 0. So x component of equation 1 as a scalar equation is V sub W plus the horizontal component of this vector, which is to the left. So I should really write minus VA slash W times sine of theta. Plugging in the numerical values, I have 20 for velocity of the wind minus 250 sine of theta. So this can be solved for angle theta as inverse sine of 20 over 250, which gives us theta as 4.59 degrees. This is the desired angle for the plane to have an absolute velocity directly to the north. Now, observe that I use the x component of the equation to find this angle. If I wish, I can write the y component as well and know what the absolute velocity of the airplane is. Suppose I take positive to be up, then vertical component or y component of equation 1, left side of it is simply VA, which is absolute velocity of the airplane. Wind has no y component, so that is 0 plus vertical component of that relative velocity VA slash WY component is VA slash W cosine of theta. In terms of numerical values, you see how I can find the absolute velocity of the airplane, which is simply 250 times cosine of 4.59 degrees. If you're interested to know what the absolute velocity of the plane is, it turns out to be 249.2 kilometers per hour. Now you can see this better if you draw a vector diagram representing equation 1 graphically. So if I draw the components of equation 1, I have velocity of the wind, which is a vector to the right, plus velocity of airplane with respect to the wind, which is this vector going to the left of vertical. If I add these two vectors, VW is to the right, VA airplane relative to the wind is to the left of vertical. These two vectors should add up to, as the equation shows it, they should add up to VA. Therefore, this is VA. And this is angle theta. Now you can see graphically how x component of equation 1 can be written. Or you can see sine of theta to be ratio of VW divided by hypotenuse, which is 250. So that's another way of looking at it, to draw the vectors in a head-to-tail fashion and have a triangle and use your trig knowledge to get what you're after. All right, that's it for this one. Thanks for watching.